questions. And then I do upload them afterwards. Typically the same day, sometimes a bit later, probably a bit later for today because I've got other things on tonight, but we'll see. If you want, you can go back through week 1 and recap. It's all here. All the content's there and stuff. It'll be fine. And just feel free to do that. And there's also a video for this too, and I'll send out an email afterwards if you missed the first shoot or whatever. Typically, for most of my notes, I'll give you a link to this in a second. There'll be answers here that you'll be able to click and look at. They're pretty similar, almost all the questions, to the actual tutes. So I guess the answers just come earlier. But the main reason that they're there is because I add extra questions sometimes. So for example, this question here, it was a pretty straightforward one, but I added an extra one that you could make it so you can see the output, right? So you can actually see the output of what the command produces, so you can compare the difference between the two, between the set of commands, right? So you can see obviously here with the -e, it produces a C file. Anyway, we're just gonna jump straight into week 2, and I'll give you a link for that. If I actually uploaded the week file, let me just double check that on my side. It is here, but did I do it right? I didn't. I'll update that link properly. Let me just push that and change. Come on, ZSH. Okay. And so that will update in probably like a minute or 2 minutes as it pushes. So we're just gonna begin. There's some int type stuff here. There's some octal stuff. There's some math stuff, and so on. And typically, what I do is I try to just cover the content at a pretty somewhat high level, probably what you'd be expected for the final exam, stuff like that. And so the idea is that it's kind of a wide range, and so we'll start simple, then we'll talk about some of the more harder parts of the content while still trying to keep hopefully somewhat approachable. Please ask as many questions as you want. Typically, the better tutes are the ones where people ask tons of questions, because they're the ones where we can kind of make sure that we answer the ones that you guys are asking. So if you have a question and you're wondering, do other people have this question and whatever, just feel free to ask it. Like, it doesn't matter. If for whatever reason you want to be anonymous, please let me know, and I'll give you like an anonymous link, and so you can change your name on that, and you'll be able to like hide your name. And I don't really want most people to do it, but if for some reason you're really, really shy and you don't want people to see your name when you're asking questions and stuff like that, I could do a situation like that for you. Anyway, I'm just going to jump straight into it. So to begin with, we have integer types. Now, most of you probably know what some integer types are, like for example, just straight up int, or maybe some of you know what long is. Most of you use a pointer, and a pointer is effectively just an integer type, right? It's just like a typical 8-byte integer on most systems. But there's many more, and the main reasons we have more is because sometimes, well, I guess it says here when should it be used, but we'll just talk about that. Sometimes you want to like be more specific about the size, right? And so, especially in the last 2 weeks, I guess you've been using some bitmass, and especially you focus around things like bitwise AND, bitwise OR, and bitwise XOR, and those 3 all work on bits, right? As per their name. And so when we want to use them, we want to be very specific. The objects that we have a very specific number of bits, because very often we perform transformations across the entire number, right? And so if there's extra bits on one side and we're iterating for every single bit, then we're going to run out, right? Eventually, we're going to reach a point where we can't find any more bits. Now, there's ways to get around those problems and so on, as I'll show later on, where we can still deal on operations on an entire integer as a whole while not caring about how many bits there are. It's much easier if we know specifically how many bits there are. And so that's kind of the main reason, as you see here, for when you want exactly n many bits. And so there's a set of types here, and you can see the minimum and maximum. You should know how to calculate these. Luckily, they're pretty easy. The rough way of doing it is you're just going to do 2 to the power of, and then you're just going to put the size here. So 8, you're going to put 2 to the power of 8 minus 1, and that will give you the unsigned variant, as you can see here. Now, if you want the signed variant, all you're basically going to do is divide it by 2, right? Now, effectively, that's just going to form 127, right? But it's also going to give you negative 128. And the reason why is weird how it doesn't like oh, there you go. So it just took a second. I don't know why that took so long to calculate. The reason why that one of them is less than the other one, and I talked about this last week, is that you're going to have to have a zero, right? And so the actual set of both sizes, the set of all negative numbers, is going to be equal to the set of all positive numbers. It just so happens that there's one more positive number than is negative, in that there's zero. And so the range for all positive numbers is going to be between let me just close down some of these awful other ones that we don't need. It's going to be between 0 and 127, and negative numbers is going to be between negative 128 and negative 1. And so the length of these sets is going to be identical, right? And the reason that obviously this is one more is just because it only includes -1, right? So that's a little confusing, but it's kind of important to still remember. So the rough idea is you're just going to do 2 to the power of the length, right? It's specified here, the number of bits. And so if it's signed, you're going to do this. And that's going to give you the total number of permutations, right? And so this is just like simple kind of permutation math that you probably did in high school. If you have like, you know, for example, the things like if you have 3 shirts and 3 pants and you want to find out the total number of combinations for your outfits, right? Well, then you can just use the similar kind of idea here, right? Where every pant can go with every shirt. And the same thing with binary math, right? If you have 3 bits, right, then you could have 111, or you could have like 000 or 101, and so on, right? And so each bit can be toggled independently. And each bit has 2 options, right? So therefore, it's going to be 2 to the 3 options. And the reason we go -1 is because we again want to include 0, right? And so because we want to include 0, the range is going to be 1 less. Right, we have a total number of permutations of 8, right? But each value of each permutation is going to be 0 to 7. It's kind of the same that an index works, right? The length of the array is +1 more than the maximum index. Anyway, now there's many other int types that exist. I presume most of you don't know them. And I'm just going to list them here. But the rough idea of it is there's exact width, as we said before. There's least width, which has a least parameter. This is effectively what you use when you want to say, I want the smallest integer possible that's at least this size. It's not very commonly used, but it can be used, especially when you care about 32-bit and 64-bit compatibility. And so you want things that are at least 64-bit sized or whatever, right? But like if you're dealing with a system where it's larger, then you're happy with it. I don't really think that you'd ever notice a difference between this and just a normal int, right? On most systems, but there potentially could be ones where it's different. And then fast is again the same idea, but it's for the fastest integer. Again, it's not really well used, but there may be cases where there could be cases where you're dealing with really small integers, like 8-byte integers and 32-byte integers, or 32-bit integers. And in cases like that, where you have really, really small integers, you sometimes pay performance cost because they're small. And so if I'm dealing on a 64-bit machine, I'm doing math on that, it has to like pad the bits such that they are the size of my system. So typically if I'm adding 2 32-bit numbers, it'll have to pad them with zeros. And that padding can technically have a small cost associated with it. It's normally not too bad. And it'll be faster than doing 32-bit arithmetic. Faster than doing, no, it won't be faster than doing 32-bit. But because of that padding, because it has to insert all those zeros when it adds the 32-bit numbers, you could get performance costs. So I don't know. Again, this doesn't matter, right? But if you're interested, the only ones that you really should care about is stuff like int pointer, which is when you're having a pointer, right? So let's say I have a pointer and I want to grab the value of that pointer, as we talked last week, right? So we talked about this last week with pointers having basically almost like 3 states, right? So we have a pointer, for example, P here, right? And P is pointing to X, which has a value of 100. Now, P effectively has 3 states associated with it, right? The first thing is the address of P exists, and you say the address of P is 2000, right? And the address of X is 1000, right? Then we also have, and we'll just make this like 5, just to make it more distinct. We also have the value of P, which is 1,000. And then we also have the dereferenced value of P, which is 5, right? And so it's important to distinguish between the 3 states, right? And so in this case here, when we're talking about int pointer T, we're basically talking about this value here. We're talking about the, well, not that value here, this value here, but we're talking about the actual value inside P, right? And so when we do a cast like this, I don't know, location of X, I guess, we could say something like this, right? And maybe we do a cast if we really want to be particularly exact. Case like this, we're basically saying grab the value of P, and we want, instead of like treating it as a pointer, we want to treat it as a number, because we want to do things like arithmetic on it, where we're not trying to just like move the pointer along. We're trying to like actually maybe like multiply it by A, or do these various other things that like are much more number based. Maybe we want to do bit math on it, like extract bits and so on. And so rather than having to deal with a pointer, sometimes it's much nicer just to deal with an unsigned number, right? Technically they're the same thing, and operations on them are the same thing in most cases. The exception being arithmetic, as we looked at last week, right? For example, if I do P++, how much is it going to increment P by, right? If I do P++, because P is an integer, right? It's going to have to increment it by 4, because it's going to move to the next integer along in the sequence. And each integer is 4 bytes. So to move along to the next integer, it has to move by 4 bytes. Whereas if I move the location of X++, since this is just like a number, it's just going to increment it by 1. So this is +1, where this will be +4. In terms of like, I guess you could call it bytes. So integer pointers are useful. They're also what you should be using. The other one that you'll probably run into too is size t and s size t, this being the signed equivalent. These are probably what you're going to see in the course later on. They're effectively just like what happens when you go size of. So when you do like size of int, this returns size t, right? Sometimes they use for pointers. It's technically incorrect, but it's typically fine. And then finally, we have int max t, which is the largest possible integer type on that system. And obviously uint max t as well. Okay, now that stuff is pretty boring. So we're just going to move on to octal and hexadecimal. And so here we have a sequence of octal characters, and we're going to look at what happens when we want to convert them to octal and hexadecimal. Obviously, I don't know, I'm repeating myself. A lot of people getting, I don't know, performance anxiety, who knows. So here we have 1, right? Converting this to octal is very, very easy. To convert this to octal, often it's better to convert to binary first, and then we'll look at tricks later on to make it a bit easier. But I almost always prefer, when I'm converting this stuff in between, to convert it to binary and then convert to hexadecimal and octal. So in this case, to convert this to binary, I'm going to just use I'm going to pretend that these are all, do they say, I'm just going to pretend they're unsigned because it doesn't really matter. The only reason it would matter would be this 200 here. If we did sign numbers, this 200 would obviously be like an overflow. So we'd have to like store it in like a large number, or we'd have to like treat it as a negative number. So I'm just going to say it's unsigned just because it makes life easier. So if we're going to do it, this is 8 bits, right? Because that would fit everything. Then this is what our bit pattern would look like for 1. Hopefully most can understand why this is, right? And I can kind of show you, if I break this up using some pieces, and then I'm also going to add an asterisk here. There's a tool that does this a bit nicer, but I don't really want to go to the tool yet, just because I kind of want to show off the step-by-step. And so if we have this, then above each one of them, we can do a 2 to the power 0, to the power 1, and so on. And so this is the way that often it's easiest to handle this stuff, is if you like kind of represent it this way. And so if we have 2 to the power 3, and then over here, I'm going to add some more spaces and these up again. This will be 2 to the power 4. I should have done this from left to right. It would have made more sense. That's okay. And then we've got 2 to the power 5 here. And then we've also got 2 to the power 6, to the power 7, right? This is 2 to the power 6. I'm going to add 2 more spaces just to make it line up. And then 2 to the power 7 is going to be the last one. Awesome. Okay. So when we're doing these analysis and we're trying to like figure out what the binary value for each one is, all we have to do is we just have to like try to match up the bits as much as we can going from left to right. And so we can represent these as their actual values. And so for example, obviously the very right one will be 1, and this one's going to be 2, right? Then we got 4, then we got 8, 16, 32, 64, and 128. And so effectively all we need to do with each of these numbers is we just have to try to figure out what's the largest number that can fit this value. And then we're just going to toggle that bit and then subtract it from it, right? This is the very simple way of doing it initially, and then later on we can go these better tricks, but it just starts simple. And so to begin with, let's not save the file. If we want to encode 1, obviously 1 just goes in the 1 slot. If we want to encode 8, right, similarly, we just put 8 in the 8 slot, and then you can just think of it in your head as subtracting 8, and we end up with 0. Now, when we want to put 10 in, we run into the same kind of issue, right? But we can't find 10. So what we do is we find, again, the biggest binary value that can fit in that value, which is going to be 8, right? And so we're going to put 8 in the slot, and then we end up with 2, again, giving us 2 in the next slot, giving us 0. Right? And you're just going to repeat this every time. And so for 15, it's just going to be, 12, for example. We can do that. 14, 15. Right? Now, there's obviously some tricks. For example, 15, you can just remember as like it's 1 off 16. Therefore, it will have every bit set below 16, just because obviously if I added 1 to this value, I'm just going to get just 16 toggled. So if I subtract 1 from this value, I would expect all these to be toggled. And this is the same thing that we talked about last week, right, with the bases and so on, right? Whereas with like base 10, if I have, for example, 99 and I add 1 to base 10, I can't represent 1 0 in a single digit. Right? I can't represent 1 0 here in single digit, so add an extra digit in front, and then the other two kind of toggle back down to 0. Right? And so the same kind of idea here, that when we add 1 to this value, it can't represent like quotation marks 1 0, or it can't represent 2, whatever, however you want to visualize it. So it gets toggled, and then the next one goes and happens to the next one as well. And so they're each trying to like carry on the bit until eventually you get, right? And that's effectively what happens when you get overflow, right? Is it's going to carry on that bit all the way to the end, and then basically it gets to this bit here, and it's still trying to carry it on, and then basically everything's toggled. So for example, if I have a value that looks something like this, I guess, and then I'm going to add 1 to this, what do you think happens, right? This is representing -1, it will be fine. Everything's okay, right? Because -1 plus 1 is defined. But if we have the largest possible value, let's say largest possible value is going to be 127, right? So 127 is pretty easy to represent. So it's going to be 100 minus 64, which is I don't know what, 63. And then the next one we're going to have is, that's right. And then the next one we're going to have is 32 and 16, so that makes 48, right? Or 32, I guess, if we want to go slow. And then that will give us 31. And then we also have 16, which is again going to give us 15. And then we're just going to get 1 for the rest, right? Because it's also 15. So as I presume most of you know, 127 is just going to be this, right? Now, if we add 1 to this, what will happen is it will toggle over each bit, giving us 128, which is okay, right? That represents a valid number. But the problem is that 128 isn't actually a valid isn't a valid signed number. So if we add that, right, and these would all, overflow, carry on, whatever, or carry on, right? And then we end up with 128. This isn't a valid signed number, right? As in, like, it isn't going to be 128 inside. Instead, we can do 2's complement to find out what the value really is, right? And so to do 2's complement, right, if you're to get a signed number, if all you're going to do is flip and add 1, to go the other way, you're going to subtract 1, then flip, right? And so effectively, what you're going to get is you're going to get, if we subtract 1, it's basically going to get where we were before. So nothing really changes, right? And then we're going to add 1, which is just going to get us back to where we were, right? So we're basically just jumping back and forward, which may make no sense, but keep in mind that now this interpretation is going to be negative. So if we add 1 to 127, then we get negative 128. Sense, right? So see how it's kind of become negative because of the side meaning, it's kind of flipped around. And so what that means is that as we add numbers to this, it's not going to go to 129 or to 130. It's going to become less and less negative and go to like negative 127, negative 126, and so on. It's going to become smaller, if that makes sense. Okay. And then the rest are similar. And so I can kind of show you it here. Let's change it to a nicer theme. And so, for example, if we have the midnight thing here, as you can see here, you can see the bits and we can toggle the bits and you can kind of see how it works. Feel free to like play around with something like this. You can kind of see how the interpretation is, right? And so in cases like this, it's taking it as unsigned, right? But if we give it negative 128, for example, we can see what negative 128 in an 8-bit number is. It's going to be 1 followed by a bunch of zeros, right? And so then if we try to add 1 to it, right, we're going to get 129 because this tool does not treat negative numbers correctly, right? That's fun. I'm going to try to fix that later. But if we go, let's say, negative 128 plus 1, right, it's going to give us an even weirder number. Oh, because it's overflowing on it. Huh. I love how I used this tool last semester. We didn't really have any issues with it. And then suddenly now we have issues. The reasons that we have issues, as you can see here, is that it's interpreting negative 128 and then it's interpreting it as this number, which is this many bits, right? And then it's adding 1 to it, and then it's getting this number because it's not treating unsigned and signed correctly. Anyway, I'm not going to worry about that. We can look at it later. But the rough idea is if you add 1 to it, you're going to get negative 127, as you can see here, and so on, right? So the interpretation here is correct. It's just for whatever reason here, how it's calculating it is wrong. Even though like the math looks somewhat correct. And so if we look here and we go, okay, let's just keep going and let's just move on to the next section because this is not too relevant anymore. But like, for example, even 200, you can do the same idea. So if we're representing 200, you're going to do 128. That's going to give you, what, I don't know, 72. Sure. And then you minus 64 from that and you can get, what, 8. And then you're just going to end up with 8. So it's going to be 122, and then 64, 8. I think that's right. 8 plus 68, 64 plus 128. Yeah, great. And so that's just the same way they can do it every single time. You mean to me? Bug in VS Code that I found last week, where if you like leave a file, it forgets that you're in the file and you have to like tool around until eventually it triggers back in. Anyway, let's keep moving. So the next thing we're gonna look at is math. This week is a bit boring week, I'm sorry. And with this week, with the math stuff, it gets a bit more interesting when we do reverse bits. There's a bunch of implementations here, but for now, it's just like kind of a math revision. And so we're just going to do a bunch of bitwise arithmetic, and that's hopefully not going to be too hard. And so to begin with, oh, I also wanted to show, I just converted binary, didn't I? Let me also convert those to octal and hexadecimal. That's a good question. I'll answer it in a second. Convert these to octal. It's pretty straightforward. I'll just grab my same value. All you got to do to convert it to octal is grab 3 bits at a time, separate them into their own chunk, add extra zeros at the front, that's okay. And then all you do is you evaluate each one by one as if it was a number, and you find out what value this is if you're converting it back to decimal. So this would just be 1, this would be 0, and this would be 0. That's all you got to do every single time. Right? And so this value would be, and we use O here for octal, and we use X for hexadecimal. Right? So if we use something that's a bit more exciting, let's say 200, right, which was 1, 1, 0, 0, 0, 0, 1, no, this, that, right? It was 128, 64, not 32, not 16, 8, not 4, not 2, not 1, and not 0. Okay, so that's 200. If we want to convert this to octal, then all we're going to do is to edit. It's really weird. I'm just going to do it in like 4 digits. I can't do it like in 3 in my head for some reason. It just does not work. So that's 128, 64, 32, 16, 8, 4, 2, 1. Okay, and then to convert to hexadecimal, again, we just combine it into groups of 3, add a 0 at the front, and then each one by 1. So this is going to be 0, this is going to be 1, and this is going to be 1 plus 2, 3. And so obviously the largest value here will be 7. So it's going to be between 0 and 7. So it's your octal, meaning 8 possible values. So the total value here will be 00310. So John asked, is there any difference between int and int16t? Yes, so int by itself, by default, is going to be effectively int at least 32. So it's going to be this, and it's going to be at least 32 bits, right? So it's going to be the smallest integer possible that's at least 32 bits, where int16 will be at least 16 bits. So the only difference between them is their size and thus their maximum value, and thus you would use them for when you wanted different maximum values. I would never probably use int16 underscore t unless I knew specifically the data was 16 bits and I wanted to do bitwise arithmetic. It's not necessarily, no, there's no difference between the two. It's not necessarily a good idea to use, well, no, there is a difference on some systems, but on most systems they're not. The only difference is that int can be larger than 32 bits. It just has to be at least 32 bits. It just typically would never be larger than 32 bits, right? This is one of those weird parts in C where it kind of like, the answer is like, typically there's no difference, but probably there could be some, right? And the same reason exists for things like null. So for example, with null, most of you think that null is equal to 0. You may not know that, but if you do know that, and that's one of the reasons why you can do stuff like this, if the pointer or if not pointer, right? Because if the pointer is equal to null, it's going to be equal to 0, and thus you can check whether or not it's true or false. But the actual C specification doesn't state this. Instead, it simply states that 0 is always translatable to null, right? So if I specify 0 as a pointer value that's equivalent to null, it does not specify it the other way around. And so what that means is that the system may define null to be a different value. So the system could define null to be like 10 or 40 or 80, right? It doesn't have to always be 0. But anyway, so this is basically how you do octal. To do hexadecimal, you do the same idea, but you just take 4 values at a time. And the only difference, obviously, when you take 4 values at a time, if I just do it this way, is that you obviously the maximum value is going to be 0 to 15, right? And so I would recommend to still kind of count it in base 10, and then you can just convert it. So this in base 10 is going to be what? Well, it's going to be 1, 2, 4, 8, right? That's okay. But this in base 10 is going to be 8 plus 4, which is 12, right? And so obviously we can't include 12 here, right? Because we can only have one space per value. And so what happens is that once we get to 10, right, we give that A, and then we give 11B, 12C, and so on. And so almost every time I do it, I end up just like counting from 10. I do remember like F, for example, and like D and stuff, but it's kind of hard to remember all of them for some reason. And so, for example, for 12, it's just going to be C, 8, and X, right? And so you're doing the same kind of idea where you're splitting up into groups of 4 because it's hexadecimal. And the reason why, if you care, is that hexadecimal is 16, and 16 is equal to 2 to the power 4, and octal is 8, which equals 2 to the power 3, right? And that's where kind of these groupings come from. And so here, what you're basically doing is just converting them to base 10 in each nibble, which is what a 4-bit pattern is. And as you convert each nibble, which is a very cute word for it, you're going to get a binary value. And then once you have that binary value, or that, sorry, not binary value, you're going to get a decimal. Is that, yeah, that's the word for it. You're going to get a decimal value. And then once you have that decimal value, you can just like look at the table that you've probably written down somewhere, or remember it if you're good at remembering things. And then you can just map it. And so in this case, I see 12, therefore I see C, therefore I can place C down. There's not been any questions really about this. I presume most people are okay with it. If you're not, please let me know. If you want me to explain in a bit more detail, please let me know. Because else, if you're confused, you're going, I got no clue what you're saying right now, and it's not great for you, right? So you're just gonna do that every single time. And so I'll do one more example just to kind of show that off. If we get, let's say, for example, 15, right? That's going to map to 1111, right? Just by 8 plus 4 plus 2 plus 1. And then to get into octal, we just grab groups of 3. So 111, 201, 000. And then once we have our groups of 3, we just convert them each by 1, right? And therefore we get octal 017. The zeros at the front aren't important, right? Just for the same reason that saying 010 or 0 like 29 is the same thing as saying 29, right? And then obviously for hexadecimal, we're going to do the same idea, and it's just going to be 000, 1111. Obviously, again, we're grabbing groups of 4, and then for each one, we just convert it as expected, right? And so this answer here would be OX0F, right? The only hexadecimal patterns you should remember is OXF being equal to the max unsigned value, and also equal to other things as well, as we'll find out later on with signed. And you can look at lecture notes too if you care. But there's other stuff we'll find out with how it relates to signed, especially when you do assignments and so on. And you can just chuck in a calculator if you care. Right? Oh, and it says here for all the shifting and so on. We'll find that later. Anyway, so that's it. Let's just move on to this bitwise stuff. The first thing that we have here is we have a bunch of patterns, and we can just convert these to binary, right? This is what you should always do. So you're just going to grab each nibble one by one and expand it to 4 values. So for example, this first one will be this one, right? Because obviously it's going to be 4 plus 1. So just expand each one by one. So this one here, this A is going to be 10. So it's going to be 1010. And a very nice way to find out whether or not a signed number is negative or not, just check the first bit, right? And first bit, if it's 1, it's going to be a negative value. So for example, if we represent this AAA, right, and we represent it as a signed value, it will be negative, right? And the same kind of trick can also be used for determining whether or not something's going to be like a hexadecimal uppercase character, right? You can check whether or not at least 10 is filled. So it had to be both these values. All right, lastly, we have got C, which is just going to be 1. Right? These are all 32-bit numbers, or 16-bit numbers, rather, because I can count here at 16. So if we do A or B, we're basically grabbing this pattern, and we're comparing it to this pattern. Now, I could do this by hand, but I think it's a bit easier if I show it here, because then I can like toggle the bits and show you what happens as we change things. So for example, with this first one, right, we have A or B, which is actually at the very bottom. It's going to go up rather than down. And we're doing OX55 and OXAAA. And so this is our OXAAA as we saw, or OX55 as we saw here. And OXAAA is the opposite way around, right? And so you can see how they're all interlaced. So obviously, when we add them together, right, since all only cares if one of the values is true, it's just going to set them both to true, right? And so if I toggle these bits, you can see that this bit does not matter. If I toggle this bit here, you can see that it turns this bit off, right? And you can see the maximum value here is OFX, FFFF, as we said before. blah. If we AND them together, however, we get a very different result because AND requires them both to be 1. Obviously, since they're interlaced, none of them are both going to be 1. So it's going to fail. If I toggle some bits, you can see that only those bits get toggled, obviously, because they're both 1. And then finally, with XOR, XOR requires either of the bits to be flipped, but not both of them. So in this case here, since they're interlaced again, only one of the bits is flipped in each row, or each column, I guess you could say. It would be each column. Therefore, therefore the result's going to be 1. If we toggle 2 of the bits, it's going to become 0 because XOR results to 0 if they're both flipped, right? So they're the 3 ones you really have to remember, and shifting as well, I guess, but shifting is like kind of easy-ish to remember. XOR is the hardest one. It's also the one that's rarely used, so that's good. And we'll see why we use them today, or probably a bit today, more next week, when we do talk about like extracting bits and so on. And so, for example, here we have OXFF and the bitwise negation, or the bitwise not, of OXAAA, right? And so the difference here with the bitwise not is we're basically just going to flip every single bit. That's all this does. And so we're just going to encourage it to actually be 16 bits, right? Where it can, just because otherwise it's going to decide to do things like not, and it's going to add the extra ones here because it thinks it's 32. So when we have the 16-bit number here and we flip OXAA, all it's basically going to do is look at every bit and set it to a 1 if it's 0, else it's going to like do the opposite. So for example, if I just restore what my thing is here, just for my sanity, it's basically going to look at all these bits of AA and flip them. That's all it's going to do. It's just going to go across and flip. And hopefully you can see that when we flip AA, we're just going to end up with FF, a 5 for 5, 5, blah, right? And so when we do this negation here, it just ends up with 5, 5, 5, 5, right? And that's it. And we're just going to, they're all going to line up and we're going to get the correct result. Now, when we shift, shifting is a very simple operation. All we basically do is move every bit to the left, and that's it, right? The key thing about shifting is that it will truncate, or rather the bits will kind of like fall off, if that makes sense. So if I keep shifting, it won't like wrap back around to the beginning. If you want them to wrap around to the beginning, you're looking for what we call rotation, and see there's no easy way to do a rotation. You have to do it manually. I'm thinking about whether or not SPIM has a rotation instruction. I don't think SPIM has a rotation instruction, but a lot of assembly languages do. So like, for example, x86 has a rotation instruction and stuff like that. They're often used for compilers. Compilers use them quite extensively to optimize certain things. But there's no like way to directly use them in C. And so as we shift this, that works. So for example, if I put a bit here, you can see it gets placed here. If I put a bit here, it's going to place it here because this will automatically extend it as need be. But if I force the insize, nope, apparently force insize doesn't. Oh yeah, it's gonna be 8. It's only 8-bit number. If I force insize to be 8, as we can see here, when I shift it, it's still gonna break it. Okay. Apparently this tool hates being told not to shift. But yeah, okay. So the whole idea here is that if you shift it, right, it will truncate and just look at these low 8 bits here. And we'll skip out this extra bit here. I'm going to make a note of these things because else I will not fix them. Shift. Okay. And then later on, we also have this one here, which just goes the opposite direction. And this one, I guess, shows it off a bit better because as we can see here, that we have 8 bits that are set, but there's only 6 bits in the output. And the reason why is that these lower 2 bits get thrown off, right? They don't come back around. We don't see them here. And then we also have the same kind of idea here, right? So again, these are just doing more complicated operations. So for example, if we want to do an operation like this, as you can see here, where we're doing this shift, right? The first step is to shift OXAA by 1, right? And so that's what it's going to do here. So it's shifted OA by 1, and then it's going to AND it with OX55, and so this is this value here. And then we're going to end with this, right? And so you can kind of like follow them through. You can like change the values and like replicate the value changes here and so on. Maybe I should automatically keep them synced, who knows? And then the next thing you have here is you have another one here where it's just doing a flip and an OR, and we can see kind of result. Obviously, if we're going to flip 1, it's going to become 1s everywhere but the first position, right? Which is quite useful, because the reason why this is quite useful is it basically lets you control what bits get set and what bits get toggled and what bits don't, right? So for example, if you want to say, I want to get every value, I want to find out what the value of this number is, except for this flag here, then this is a good way of doing it. And the reason why this is awesome is this allows you to toggle bits. So for example, you could turn a certain bit off this way. Because as we can see here, it doesn't change the number whatsoever except for this position. So that allows us to turn that bit off. And so with OR here, we get a similar result where they're able to like turn this bit on. So for example, if this bit is off here, it would now turn it on, right? So basically, OR is typically used to turn things on, and is typically used to turn things off, right? And for the same reason, OR is typically used to like write to a value, and is typically used to read from a value, right? Because obviously when you're reading, you want to turn off everything but the bits you care about. Yeah, so that's basically it. You can go through that if you and look in more detail. Now there's a section on logical versus arithmetic shifts versus rotation. You can kind of read about it. It's kind of somewhat complicated. Effectively, on most systems, the rotation, the shifting depends on your type. So, for example, if we have as you can see here, if we have a right shift, it's going to divide, and if we have a left shift, it's going to multiply. But the problem is what happens is if you got an unsigned or signed type. So for example, a left shift, and we do a left shift by like an unsigned number, right? It's just going to wrap around, and that's kind of it's not going to wrap around. Rather, it's going to like modulus that value by the maximum, right? So what that means is that it will effectively it's kind of, I guess the rough ways, it's kind of can be thought of like it overflows correctly, if that makes sense. So it will just handle that properly. So for example, if you go it's a good example here. uh, Not necessarily, but you can kind of, if we keep this to 8 bits, what will happen is the number will get too large to wrap over, and so it will just kind of, the value won't come back to the start. That's rotation. But instead, what will happen is that you can think of like the actual result value will kind of get wrapped. Um, and so for the same reason, I guess a better analogy of it is if you have an unsigned value like this, for example, uh, we have 255, and we add 1 to 255, the result of this is 256. Now, this is bigger than total set because we can't actually represent it. So what it's going to do is effectively going to do a modulus by 256, which is the largest possible value, and that's going to cause it to wrap around to 0. So the bits aren't wrapping around, the value of those bits is wrapping around. And so, for example, if we have 257, it's going to become 1. Right? If we have 250, like 280, right, it's going to become whatever that is. I can do that math. I don't know why I didn't. And so it's just going to kind of get that wrapping behavior. The next thing we have here is we have some other things talking about what we call undefined behavior around sign numbers. Sign numbers have undefined behavior for overflow effectively. So as long as it doesn't overflow, it's perfectly fine to like shift it by left and right. But as soon as overflow or underflow would occur, it's technically not well defined, but it will typically work, right? And so the only case where it won't really work is if you do division, as you can see here. If we do division by 2, the result of that, if it's less than 0, so if we try to divide a negative number, right, and then the result of that will kind of be weird. And typically, as I said here, we'll just do a arithmetic shift, right? And so effectively what that means is it carries the 1, and so it will typically work kind of the way you expect it to, but it is a little weird. And so just try to like, you can open up a C compiler and just try to like play around what happens as you shift negative numbers and so on. But I can kind of show you roughly what would happen. So if we have, for example, minus 200, and we do a right shift, right? And I'm going to do 3 right shifts just because in this system, that's what defines a rhythmic shift. Else it would not do it. And I shifted by like, for example, 2, right? We can see what's happening here is is it not gonna, is it, I don't remember how I defined rhythmic shifts. There's help somewhere that tells me. All right, and so what we can see here is we've got minus 200, which is equal to this. And so when we shift to here, it's not actually shifting the bits properly. But typically it should include extra minus ones and stuff, so it would work and how you expect, right? So it would be like minus 100. This is just like a typical binary shift. It's probably just because it's thinking it's unsigned. It doesn't really matter. You can check open C compiler and run it if you care. Emulating C is really hard in a browser because there's no such thing as like controlled integer sizes or arithmetic and stuff like that. So you kind of have to like emulate it, like using strings. It's really messy. What we have here is we have flags, and so we're going to look at flags and then lab intro, and then we won't really have too much time for this, but we will talk about it slightly. So the lab intro is where I want to begin with, and I'm just going to look at this part here with the string tool and roughly go through it for the lab. And so on the page where we do this. And so what it does is it's going to convert the first argument here, or arg, which will be most likely the first one, and the second one, and so on, right? It's going to convert it to a long number, right? That's what it means, string to long. And then this null here is typically what's called like an end pointer. And so if I open up the man page for string, I can find a bit more information about it. And you should always use a man because it will help you a lot with figuring out what these things do, and also figuring out like how the arguments work, and especially the weird under highlighting behavior. So for example, this is 16 out, isn't it? Yeah, it is. So if we look at 16 out, and there's this file here that we can look at, and you'll just be able to download it. We can see that what it does is it goes through every argument, as I said. It converts it to a string toll. It grabs the output of that. So you can think of it like it converts a 16-bit signed integer to a string. So what's happening here is it's reading in all the strings, converting those strings to a decimal value, like 24, 28, and so on. And it's converting that value to the pure binary bits that represents that value. And so what you'll have to do is you'll have to that's so weird. I'm just going to open up SSHDC and just do this. So if we look at string call here, we see there's 3 things. There's an end pointer, base, and an end pointer, right? And so effectively, the end pointer is the input. So in this case, the argument. The end pointer is a pointer to a pointer, right? And so what this will do is this will modify this value here and point it to where it stops reading from. And so we use this quite a bit when we want to like determine whether or not the reading was successful. Because obviously if we finish reading the entire number, this will be pointing that null. And so we're able to basically determine where the reading stops. It can also help if you're going to read a bunch of integers in a row. And then the base is just like the base of the number, right? And so we can see here that it's going to be between 2 and 36. So typically it's going to be like 10, for example, right? But it seems like it's returning 0 here. So we could probably have a look through here and figure out what the 0 actually is representing. But it's saying there's a special base here called 0, right? And so we can see here, the string may begin with an arbitrary amount of white space, followed by an optional plus or minus sign. If the base is 16, it may include a 0x. Otherwise, a 0 base is taken as a 10 decimal base. So what this is basically saying is this number, this 0 here, is quite special because the 0 base can be taken either as octal or decimal or hexadecimal. It supports all 3. So basically, if it's hexadecimal, it will start with an OX. If it's octal, it will just start with a single 0, which is the old way of doing it. And if it's none of those 2, it will be base 10. So this is kind of like figure out the base. It's like calculate the base yourself, you can do it, right? And so you guys don't really have to know too much about that, but that's kind of cool. So it means that when you're testing it, you can give it like hexadecimal numbers, You can give it like negative numbers, positive numbers. You can give it octal numbers. I typically, it probably will work with giving it a negative octal rather than like requiring on the octal to like produce a negative result. I presume that works, but you'd have to test it. I've never particularly tested that. Anyway, so that's all you got to do. So for example, converting this number to a 16-bit number, we'll find out kind of what you're meant to do when we look at the reverse bits part, right? Flags is not really important for this lab. So often I skip it, but I do just want to give it a quick check. Yeah, so this lab, especially this week, is a bit shorter. It's basically just like 16 in, 16 out, followed by converting BCD values. So this is basically how this works is that you're just going to be looking at toggling bits and so on. So we'll be looking at this next week. And you can see the answers here below if you really care. You can try like do them yourselves. But I can kind of roughly go through in like 2 minutes how this works. So if we want to, for example, mark as something for locked as for reading blocks, right? The first thing we're going to do is we've got to mark as locked, then we go to mark as reading, then as blocks. And the way we combine bit flags, as we can see here, is we use the or sign, just as I said before. So or is used for like writing to something, for modifying something. It's used for combining stuff. It's used for anything that's like kind of add to something. It's basically like addition in bitwise arithmetic, right? And this is the result here. And same thing for writing. Now, if we want to set it as locked, but we don't change whatever the current values are, we just want to modify or write it as being locked. And so all we do is we just modify x and we just do or equals. You could also do like something like x equals x or locked, for example, or you could just do x or locked if you want to like place it somewhere else, like a printf, right? However you want to do it. And then the next step is remove the lock. And so if we want to remove the lock, we'll talk about what I said before, where you can use the and to basically remove something, right? So the and will obviously, if we use the and in the bitwise not, it's going to flip it, right? And so it's the exact same thing as we saw up here with the bitwise not. Here, where I said, remember I said before about like how this will make sure that this bit is toggled off if it's not within this set. So if we look at the one that uses OX1, for example, this is the better case. If this bit is toggled, it will forcefully turn it off. Right, oh, sorry, if this bit's toggled, it will forcefully turn it off. You can see here. Because the bitwise AND is stating very explicitly that the range is only going to affect left to right here, right? Because it's everything but 1, basically. So every other value remains unchanged but this first value. And so for that reason, when we want to do it here, we're just going to say AND equals. Now, if we want to toggle, we're going to use the XOR. And that's the same reasoning as set up here, right? With the, as I said down here with the OR, is that if either one of them is true, it's going to turn it on. If they're both true, it's going to turn it off. So this is toggle on and off. And then finally, we have this last one here, which is, hey, if we're in read mode, go to write mode. And if we're in write mode, go to read mode, right? And so for the same reason, we can basically just chain XOR, right? And so this will swap both of them. So we can like chain multiple things at once for the same reason. Okay. And then finally, what we have here is we have a slightly more complicated way of doing it. If we want to basically not do anything if it's in read-write mode. For example, if it's in read-write mode, we're saying we don't want to do anything. So if it's, for example, we're reading and writing and we toggle reading and writing, then we just want to stay the same. Because obviously, if we're in read mode, we're going to go to write mode, and if we're in write mode, go to read mode. So if we're in read-write mode, we don't want to modify anything. But something like this would modify it most likely. It would toggle both of them off, right? So this is technically not 100% correct. And the way we can do that is slightly more complicated. And the rough way of what we're doing is that we're just kind of going to be the trick here with the off thing, right? So what we're doing here is basically saying keep every bit that you had before, right? So this is just going to grab every bit that doesn't include reading and writing. And so this is the same logic as we did up here, right? So this is basically our safety check. This is just going to be everything else. And then this part is what we're going to do to basically access it so that we specifically do it so that we toggle the bits in a bit of a nicer way, right? And so effectively, we're going to grab the reading bit and we're going to move it into the writing position. So in this case, writing is at OX2 or the second bit and reading is at the first bit. So when we want to switch reading to writing, we're just going to move it to the second bit. we want to switch writing to reading, we're going to move it to the first bit, right? And there are other ways you can write this, but this is just a simple way of writing it. Whereas something like this, because it's going to toggle it, it's just going to toggle both the bits off, right? So, if they're both set, they're both going to become false, which is not what you want, right? We want to obviously swap the reading for the writing for the reading. So if it's in read-write mode, it just kind of like swaps them back and forth. So nothing changes. And we use OR to combine each of these sub-components. Okay, finally, we're going to look at reverse bits, and we're going to look at the important parts for your lab, right? So I typically will probably go 10 minutes overtime with this because I don't know, it's just a bit slower today. So there's a few ways we can reverse bits. And if you care, you can look through, there's 3 methods here. And at the very end, I talk about performance benchmarking this. And so you can look at the performance of each one, and you can look at the results, and there's a bunch of analysis of this stuff, like talking about what's the performance of each of them and talking about why they're slower and so on. But the main one that I want to focus on is there's 2 basically ways that you can write this code, and they've got different ways of thinking, right? And so I'm just going to open up a document and we're just going to write it, and then we can look at what it means, right? Okay. I can get up the question on my other side because I don't remember. It was reverse bits, but I remember what the input is. Okay. I don't have the input here. It doesn't matter. Okay. So it's going to begin. I'm just going to copy definition, and we don't care about this comment here. So the simplest way is if let's say we know what the size of the value is. So as I said before, if we don't know, it gets a lot more complicated. But let's say we know it's going to be 32 bits, right? Which is going to be your lab. You're going to know it's 16 bits. If we know it's 32 bits, right? Then the easiest way to reverse the bits is basically just swapping each one, right? So for example, if we have a bit pattern like this, we're just going to grab each bit and swap it with the opposite bit, right? So let's just make sure this is 4x4. Yep, okay. So in this case, it's swap the one with this one here, right? Now, if this is a 32-bit number, obviously it's going to swap this one with the very first value all the way on the left over here, 31st bit. But if this is only an 8-bit number, it's only going to swap this one here. And so what we're going to end up with is we're going to end up with 1, 0, 1, 0, right? 1, 0, 1, 0, because these bits get swapped. And then the other series of bits are all going to be zeros, because basically it's just going to move these to the front, and then the other bit's going to be flipped. Okay. And then we want to basically just do this one by one for each one. So the easiest way to do it is just to iterate through as if it was like an integer array, right? But each integer value can only have a 1 or a 0. We're going to go through each bit one by one. I'm just going to use an int here. There's other ways you can do it too, but we're just going to use I, and we're just going to go through each 32 values, right? I plus plus. And then for each value, what we're going to do is we're basically going to treat it like an array, as I said before. So we're going to create a way to index the object. Now, indexing the object is a little interesting, right? It's not particularly easy. But we have 2 tools at our disposal. We have AND and we have OR. And I talked about it before. We have AND for extraction and OR for writing. Because AND extracts just the bits we care about, and OR combines just the bits we care about, right? With everything else that also remains the same. So to extract just the bits we care about, we want to think about what specific bit in this case do we care about. In this case, we care about the bit from the right and the bit from the left. But an easy way we can do it, rather than swapping the bits within the word, is we can just move each bit into its correct position one by one, right? So rather than have to swap all the way through, we can just move the first bit into the very first spot here in this word and so on, right? So it means that we don't have to swap them. We can just like move them into the correct position one by one. It means we're doing more work, but it's simpler. So to begin with, right, we're going to do a writing operation. Right? We're going to write to this object. But many different ways. Right? effectively, if this was an array, we would want to write something like this. Yeah, I guess there's many different ways you can write it, but like maybe you want to do like 32 minus I equals word of I, right? If this was an array. Now it isn't because we can't index it by bits. We only index it by bytes. So instead, we kind of have to simulate this behavior here. And so what we're going to do is we're going to first extract the bit we care about and then move it into the correct position. So the bit we care about is I, and then we're going to move into this position offset from the left. So easiest way to extract the bit is just to basically do 2 or 1, sorry, right, 1 shifted by I. And so the idea here, and we can just like store this in temp, is that it's going to grab only the bits we care about, but first create a mask, that's what the typical word for it, that matches only ones in the positions that we want to extract from. And so in this case, we're going to move 1 from the first position, and we're going to move it by I. So for example, if I is 0, it's not going to move at all and just extract the first field. If I equals 1, it's going to move it by 1. If I equals 2, it moves it by 2. If I equals 3, it moves it by 3. Right? And so it's just going to keep shifting that left and left and left away until it reaches whatever position it needs to reach. Okay. And then the next thing we want to do is we basically just want to place that into the right index. Right? And so, well, we know what 32 minus I is. That's pretty easy to calculate, right? But how do we place this into the right index? And this is where it gets a little bit more tricky. And the problem here is to do with the fact that when we AND this with our value, we don't reset the position of everything. So for example, if we have a bunch of ones like this, when we AND them together, all we get is just this bit here, but we get it in the first position, which isn't very useful for us, right? Because all we really want to know is if it's toggled or not. So what we're actually going to do is we're actually going to grab this value here, right? And this is quite common, and we're going to shift it back. Right? So we've shifted it forward to find the position. We've got the value, and then we're moving it back. You can think of it like an arm, like a robotic arm, right? That's moving, grabbing pieces. It's lifting up, it's growing across, it's grabbing the bit that you want, it's lifting that bit up, and then it's moving it back, and then that's your value, right? And the act of moving the arm left and right is these shift operations. So it's shifting it back and forth. And so now once we've shifted into position, all we want to do, and we'll see in a second how to make this more terse, but for now it's fine. All we want to do is we basically just want to write this back into the position if it's true. So we can check something like this. We go, hey, if temp, you could say if temp equals 1, and because again, we moved it back into the position, so it's either going to be a 1 or a 0. If we didn't do this operation here, this value is not 1. This value is 8, right? 1, 2, 4, 8. So in that case, we'd have to check if it's basically just greater than 0. Another way of doing that would just be saying if temp, or if temp does not equal 0. Technically, if temp does not equal 0 is more correct to what this if condition is, right? Okay, so now once we've done that, we've gone, okay, we've made sure, I guess I'll write this just for people who are going to copy this. So we're checking if temp does not equal 0. We're basically going, hey, as long as we're not a fully zeros across the board, and we've got at least one bit somewhere, in this case, because we shifted it back, it's always going to be in the first position. I want to set that equivalent bit in red. So it's going to do a set operation. As I said before, that's using the OR. And then all it's going to do is just move into the correct position. So we're going to grab temp. We're just going to shift it back by 32 minus I. Right. So what we immediately notice here, I guess you could say 1 actually, because we know temp has to be 1. It's technically a bit better to do 1. What we immediately notice here is we notice a pattern between what index operation is and how to index it in a bitwise arithmetic way. And the same thing occurs. Can people see the screen? I can stop sharing and re-sharing. Oh, sorry. How long was it gone for? Okay, I'll re-talk about what I was saying. Cheers. Okay, so what were we up to? Did we do the if statement? I presume we didn't. Let me just redo that. I think it's worth covering it again. Okay, what's an if? Awesome. So we'll just kind of rewrite it from scratch. So as I said before, if there's 0 and stuff, right, we want to check it's not equal to 0, because if it's equal to 0, then that means that the bit isn't set. So there's no point us setting it, right? So what we're going to do is we're going to specifically set the bit by using the OR. Or is like a setting operation. I will very often shorten this form to just or equals. It's just out of a habit. I try not to in the notes because I know it makes them more confusing. But if you notice stuff like that, that's why. And you can do the same thing with obviously plus and greater and shifting and so on. And so we're just doing or, but now what we want to do is we want to grab an index that's equal to 32 minus I, and that's the position that we're putting in. So we're going to grab the value 1, and we're going to shift this by our index, right? And so our index here is 32 minus I. That's all we're doing, right? It said 10 seconds ago, but it was off. The index is effectively associates with what you're shifting by. And so that just repeats for everything. So the same thing for like here, where we're shifting by I, because we're getting the right position. So I'm not going to go too much more, but I will show 2 more ways of doing it that's quicker, like, and makes a bit more sense in terms of like maybe you're thinking. But anyway, so this is the rough way of how it works, and you can return right at the end. This should be fine. I don't see any errors from it. And so basically what we're doing is we check if each bit is 0, and if it isn't 0, as you can see here, we're gonna be setting the correct bit. Now, the problem here with this kind of coding tool is that, especially with stuff like this, we can use various tricks to basically avoid us having to determine whether or not we have to actually do this if statement, which is kind of clever. And so this is just kind of every shoot, I typically like introducing a topic that's outside of the material, just because I think it helps bring things tied in together. And so you can see some craziness here where this is a kind of a nice trick. I'm going to explain what this does in a second, right? This is just like 32 minus I, right? 32 minus 1. Oh, that is actually one mistake I did make. 31 minus I. And the reason why it's 31 is because this would be 31, right? Because obviously you want to, when you're finding the index from the ender array, you're doing length minus 1 minus I. That's how you find like the index from the end. And so the same thing happens here. So the first index you want to be 31 and the last index you want to be 0, rather than the first index being 32 and the last index being like 1. Another analogy would be if I'm going down an array, I do this, right? Where I start at 31 and I stop at 0. Anyway, and so the other way you can do this is using this trick around not, and I think this is quite nice. And so the idea is that we already know what not does for booleans, right? So if we go not false, for example, or in C it would be 0, most of you probably know that goes to 1. And not 1, if you don't know this, it's okay. I don't know if they teach in 1511 anymore. If you go not 1, it goes to 0. Right? Technically, if you go not x, where x is anything but 0, it will go to 0, right? Because true represents any non-zero value. And so when you do a double not, right, you effectively coerce value to be either 0 or 1, which is kind of nice. So in this case, for example, this 0 maps to 1. So when we do a double not, it goes to 1, which goes to 0. It's like we haven't done anything, right? But when we do a double not x, it goes to not 0, which goes to 1. So we've converted a value that's not 0 into a value that's simply just 1. And so what this allows us to do is it basically allows us to determine whether or not stuff is 1 or 0 without having to do things like if statements and stuff to check it. And so you can kind of see it here, right? All it's basically doing is doing a double not, and it's got the same mask, which is just what we did before, right? So the mask is just this temp, right? But the difference between the mask and temp is that it hasn't actually, the big difference here is it's going from 0 up and it's doing a subtraction to do the same kind of thing as what we're doing up here. We're shifting it by I, but instead it's going backwards. So it's going from up downwards and it's writing to the lower bits. So it's getting the value from here and then writing to lower bits. And the reason why the double knot is great is because of this problem that we discussed here, right? Remember how we said this value is 8, it's not 1 or 0. So by using a double knot, we're basically coercing this value to be a 1 or 0. You could also just use a shift. So a shift here is going to be the exact same thing as a double knot, right? The only difference is that double knot allows you to coerce any value, where shift is only specifically for when you know what bits are set. So you could also just do a double knot here on this value and not need the shift. Right? You still need the if statement unless you're in a case like this where we don't need the if statement, because what we actually find out is if we just put temp here, right? If this is 0, it's just going to write a 0 into the position, isn't it? Because it's just going to go 0 shifted by this. If it's 1, it's going to shift a 1 into position. So as long as this is either 1 or 0, it doesn't actually matter. And so what this means is that this if statement is not actually needed, right? If temp is 0, it will do nothing. If temp is not 0, then we know it has to be 1 because we're doing the shift here, or we're doing a double knot or something like that. The case would be is if you don't want to do the shift and you basically just want to do something like this, right? In a case like this could be 8. It could be anything, right? It's just non-zero. So in a case like this, we do actually have to specifically check. So in bitwise arithmetic, there's like a billion different ways you can do things. So don't care too much how you write it. So there's other ways here. I'm not gonna go too much more, but this way is like a conveyor belt where basically it grabs each bit and it shifts it one by one and basically shifts the entire number down, as you can see. So this is our number that we're reading from effectively, right? And we're going to copy the rightmost bit, which is 1 here, and then we're going to shift it left by 1, and then we're going to read the next one, right? And then we're going to shift it left by 1. As you can see, the whole number just keeps getting shifted down, allowing us to basically write the number into place, right? And effectively, and so on, at the very end, we're going to end up with a read number that looks like this. So you can see we shift into place, and then we grab the next value, which is 0. We're going to move into place, shift it by 1, grab the next value, which is a 1, move into place, shift it by 1. And so basically, it's like a conveyor belt as it moves each number one by one and shifting it. So the difference is that the difference between a case like this and a case like this and other algorithms is that something like this can stop a bit earlier because it will stop until there's no ones left. Where a number like this has to go for every single value, right? So there's various different ways. And something like this, it's just going to keep shifting while the word does not equal 0. And then we just shift by whatever's left at the very end to move it into the correct position as like an optimization, right? And there's other ways too. I think this was one in the Tute that they talked about, and you can read through it. There's a lot of comments, so hopefully it makes some sense. But the rough idea of this is that you have 2 moving masks that move left and right. And as you can see, the actual code for this is very simple. Like it's very short, and it's a dictionary. And effectively all it's doing is it's moving you got 2 like 1 masks, and one moves left and one moves right. And you basically use it. So you read it from the left mask and you write it to the right mask. So you basically read from this mask and chuck into this mask over and over again. And it's effectively the same idea as here, right? But instead of having to recalculate this every single time, you're just moving it left and you're just moving the other one right. And then we can look at the optimization of each one, right? So there's other ones here too. There's some other ones, for example, this one uses no condition, whereas this one uses a condition. And I use multiplication to avoid the condition. And then you got things like here, like this one uses I don't remember what built-in FFS is. It's like last year. Is it? Returns the index of the least significant 1 bit. So basically returns the position of where the first 1 is in the number. So obviously it doesn't have to start from anything past that. So if the 1 is in the very last position, it won't analyze anything to the right of that. And then it just does the exact same logic here, right? And so it turns out that the fastest one, you can see this is also technically a library I wrote, and there's a link to it somewhere. You can see it. And see if you run it through it, you'll get this analysis. You should be able to just basically, there'll probably be a file somewhere that you'll be able to run, like here. And so if you want, you can just compile the example or bench algos actually. If you compile bench algos, you'll be able to see the results of it. And it basically just says a bunch of things. It uses volatile, so make sure that these actually get modified on every loop. Volatile is just a keyword to basically say every time you want to read and write from it, you can't like cache that value somewhere and like say, I already know that value, you have to read from it again. It basically forces the system to typically do less optimizations around trying to skip running or executing it. Because if you're trying to test how fast it is, right, you don't want to just go, well, I've already calculated 10 times. This is a loop that doesn't change every single time. Like as you can see here, it's just doing the same thing over and over again, right? And the reason why is because the operations itself is so fast that just doing it once is typically not enough. And so you run it a bunch of times, and then you run that a bunch of times, and then you like average the results. But anyway, so when you're doing stuff like this, what you want to make sure is you want to make sure the performance of this is fine. Anyway, and so we can see here that it's, if we reverse the bits and we copy one by one, which is the very first code example, it takes 3 seconds to do it however many times it runs it here, right? Which is quite a few times, I think. It runs it that many times. So as you can see, it's pretty freaking fast, right? And the main reason why is because it's only 32 bits. So it takes that many times to run it in 3 seconds. So it's a couple, nanoseconds or something each. I don't know how many zeros that is. And then if you copy bits one by one this with no branch, if you do it with a branch, it's even faster. And the reason why it's faster for a branch in this case is because the branch is quite common to be taken in larger numbers because it's a 50-50 chance basically, but typically values which have ones closer to it, so the branch predictor does have a nicer time. And not only that, if you actually look at we'll look at MIPS later on, and I'll probably come back to this when we look at MIPS. And if we look at the branches that produces from this if statement here, we'll actually find that the branches from this if statement will be more efficient because all it's going to do anyway is just loop back to the beginning of the for loop. So it's basically just doing an earlier loop. And so the performance is about the same because of that reason. Anyway, I think it's 2, and you can see that if you use two cursors with no branch and that optimization of FF, you can see you get about 0.382 seconds, which is about 10 times faster. And there's some analysis here, and you can just kind of see a bit more in depth of what the actual specific times of each one was. That looks a bit nicer. And you can also see why these are slower. So anyway, you can look through that, and if you're more interested, it's an entire field called data-oriented design, typically, and it's all basically around. I mean, this isn't necessarily data-oriented design, but it is kind of something that people do in data-oriented design. It's about like trying to keep your data really close to each other, so making the cache really optimized. So like if your data is really close to each other, when you're accessing one bit of memory, the computer will try to think that you're going to keep accessing memory near it. So it'll load the memory near it into the cache. And so when you access future bits of that memory, it's already going to be loaded. And so that's much more efficient, right? And so the same reason typically they use a lot of bitwise arithmetic and stuff like that, because they want to avoid branches. And avoiding branches is a big part of data-oriented design. Anyway, so you can kind of see the rough idea of how you do that. And so tricks like using multiplication, because obviously if I have a 1 or 0, the multiplication is going to produce either 0 or right. And so this lets me basically say, set it to right if this equals 0. If it is equals 1, then set it, sorry, if this equals 0, set it to 0. If it's equal to 1, set it to right. So it's basically an if statement of how you need to write an if statement, right? But even with doing this, it's less efficient. And this is another way you can also write it too. And both are, this is technically faster, but both are pretty inefficient. And the main reason why just comes down to the fact that the difference between this one and this one is that with this one, you're having to do 3 extra operations, right, on top of the operations you're already performing. And one of them is a multiplication, which is more expensive. And so just overall, you're just doing more work to avoid a branch, and the branch isn't that expensive, right? Because the branch is basically just checking if it's 0 or not, and checking if it's 0 or not is one of the fastest branches you can do. So anyway, I went over time because that's interesting. And the rest of this stuff was covered last week.